Assalamualaikum and happy greetings to all. My name is Shasha Farina binti Zulkifli. Together with my partner Khairil-Anuar bin Ahmad Roni, we will be presenting on our project for subject MKEL 1123 Advanced Microprocessor System. Our project title is Implementation of Interior Car Noise Cancellation System using Digital Adaptive Filter on STM32F410RB. So here are the list of contents for our presentation. So for my parts, I will explain from introduction, problem statements, objectives, literature review of previous work, and flowchart. For the rest of the presentation, methodology, results, and conclusion, Anwar will be explaining. So first, let's go to the introduction part. For the past few decades, we can witness the automation engineering field has made a massive progress in building a built-in system in most of the automotive vehicles. This can be seen where more than 90% of the system in automotive vehicles are microprocessor and electronic-based systems. Although we are all depends on the computer-based system, internal car noises can cause irritation and disturbance to human hearing. One of the examples is internal noise produced from any system such as brake system, fuel system, exhaust system, engine system, and many more. Thus, to ensure the driver and passengers get a smooth ride experience, a noise cancellation system with the concept of digital adaptive filter has been implemented using ARM Cortex-M microprocessor. So first, I will explain what digital adaptive filter is. Adaptive filter is a digital filter which estimates coefficient of the filter according to a given criterion, where the criterion here is referring to desired signal. So the filter consists of two parts. The first part is a digital filter which is used to filter input signals, and the second part is the adaptive algorithm which will adjust the filter coefficients. I will explain more based on this diagram. So from the below diagram, this Xn is represented as an input signal. So from in this project, the input signal is represented by the internal car noise. So the next is Yn. Yn here is represented by output signal of the digital filter. Dn here represents as the desired signal, and lastly En represents the error signal. So first, the input signal Xn will be detected by any input component, for example, microphone, and it will driven to the input of the digital filter. Once the signal has been filtered, the output come out as Yn will be subtracted from Dn here to get the error signal En. Then the error signal will drive the adaptive algorithm. So the adaptive algorithm we use in this project is the LMS algorithm. So this LMS algorithm I will explain in the next part. So this algorithm will generate the filter coefficients to minimize the error signal produced in order to get a result close to the desired signal. So the next part is adaptive algorithm. This adaptive algorithm refers to the LMS algorithm as I mentioned just now. So this algorithm is being created in 1960 by a professor from Stanford University named Widrow, together with his student Huff. So this algorithm has been widely used in various adaptive filter applications such as noise cancellation, image processing, and etc. So many researchers use this algorithm due to its simplicity and the robustness. So this algorithm is a very simple algorithm used to impersonate, or in other words, to mimic the desired filter by finding related filter coefficient to produce LMS of the error signal. Next, I will talk about the problem statement for this project. The main problem is when any one of the automotive system produce internal noises due to some problem, this internal noise can cause disturbance and discomfort to driver and passengers. So how we want to tackle this problem? By implementing a simple and low-cost method that can help to attenuate the noise. So move to literature review and previous work section. Below table shows some of the previous work and research on noise cancellation system. So in the table, you will find the topic of the paper, the year of the paper has been published, the algorithm used, and also the platform used. So for the first paper, active noise reduction by the modified LMS algorithm board level experiments. So this paper has been published in 2014. So in this paper, the author used modified LMS, which is modified least mean square algorithm, and this algorithm has been implemented on Arduino Uno board. For second paper is on the LMS adaptive filters for noise cancellation, a review. This paper has been published 4 years ago on 2017. So from this paper, the author actually tried to find the best algorithm used for noise cancellation system. That's why we can see the algorithm used are Weiner, Kalman, LMS, and LMS, and also RLS. In the end, the author concluded that LMS is the best algorithm to be used for noise cancellation system. The next paper is on implementation of the LMS algorithm for noise cancellation on speech using the ARM LPC2378 processor. This paper has been published in 2009, also use LMS algorithm as the adaptive algorithm. This algorithm has been implemented on ARM LPC2378 processor. So for this processor, is a 32-bit ARM7 processor with many other features, such as it has frequency up to 72 MHz, it has 512 KB on-chip flash ROM, it has CPU clock up to 72 MHz, and many more. Compared to the ARM Cortex-M4 board that we use for our project, which is STM32 board, STM32 has higher CPU frequency compared to the LPC processor, where STM32 has maximum 100 MHz CPU frequency. However, STM32 has lower flash memory compared to LPC, where it only has 112 KB flash memory. So for the last paper on solution for vehicles noise cancellation with modification of LMS adaptive algorithm has been published almost a decade ago on 2012. This paper also used LMS algorithm as the adaptive algorithm. So for this paper, the author focuses on finding the best algorithm for vehicles noise cancellation based on LMS algorithm. And those analyses were being monitored through MATLAB software. So based on the list of papers in the table and also some papers that we have found, none of the paper has used STM32F410RB board. So thus, we decided to use this board and see if it will give the best solution or the best platform to reduce the car noise. Okay, so I will explain for the last topic for my part, which is on the flowchart. So here, the flowchart will show the overall flow for our project. So the input noise here is represented as the car in noise. So first, the car noise without the car moving will be detected through the microphone. This raw input signal will be displayed on the monitor, which represent as the desired signal, which is the end here. After that, the car will be moving and the input signal will be captured through microphone connected to the ARM Cortex-M4 board. Then this input noise will be filtered by using adaptive filter and analyzed using STM32 mix platform with the help of CMSIS DSP library, which contain the adaptive algorithm, which is LMS algorithm. Once the input signal is being filtered and analyzed, the spectrum of the LMS of error signal will be displayed on the monitor again to see the differences between the signal has been driven by the algorithm and the desired input signal. So for the next part, Anwar will continue explaining.
Thank you, Shasha. Next, I'll be presenting the methodology, results, and the conclusion of this project. For our methodology, we're using ARM Cortex-M4, or specifically the nucleo board F410RB. What is ARM Cortex-M4 actually? It is actually a processor that is being developed to address a digital signal that can demand a very efficient and easy to use signal processing capabilities. In our case, in our project, we're using it as a filter through the CMSIS DSP library. It is also a high efficiency signal processing functionality but with low cost, low power, and ease of use benefits of Cortex-M processor family being used in various industries for motor control, automation, and power management. And this is the ARM Cortex-M4 layout. As you can see, the CPU consists of ARM v7M. And this is the hardware that we're using. Next, the software that we initially use is the STM32 Cube MX. It is a graphical tool which allows easy configuration of STM32 microcontrollers and microprocessors. It actually generates the C code for ARM Cortex step by step. However, we are no longer using this software and we have replaced it with the STM32 Cube IDE instead. Next, the library that we're using is through CMSIS DSP. CMSIS stands for Cortex Microcontroller Software Interface Standard. It is actually a hardware with the abstraction layer developed by the ARM company for microcontrollers that are based on ARM Cortex processors. It also provides the interface from the processor to the peripherals. It also includes the delivery mechanisms for devices, boards, and software. It consists of 10 components. The components that we are using is DSP. What does DSP stands for? DSP stands for Digital Signal Processing. In this, the DSP library consists of more than 60 DSP functions for various data types. Mostly, it uses fixed point, single precision floating point, 32 bits. It is also optimized for SIMD instruction sets available for Cortex-M processors, which we are using in particularly. Filtering functions is the main concern for this project. Thank you, Shasha. So next, we'll proceed on the steps on how we enable the CMSIS DSP library in IDE. Okay, so there are a couple of steps. So the first step would be to download the library from GitHub. The link is down below, and that is the library that we'll be using, arm_math.h. Next. Okay, the second step is to download the precompiled object file from GitHub as well. And the link can be found as highlighted below. The third step is to add the library in the IDE software. You have to copy and paste the file from step 1, which is the ARM math, into the include file in the project created folder, which is as per the snapshot, it is in the core include file there. Then, after you include that file inside the project created folder, you have to refresh the IDE, and then it will display that the arm_math.h, the header file, will be available for usage. The fourth step is to include the library in the code by using hashtag include arm_math.h, and we need to also define arm_math_cm4. The fifth step is to link the precompiled object file to the library arm_math.h on the leftmost on the screenshot below, highlighted in yellow. So what you gotta do is to right click the arm_math.h file and press on properties. When you open the properties, on the right side, this will be pop up. Under C++ build, go to settings, and then it will display this MCU GCC linker, and from there press the libraries, and then in the library search path create another folder named libs libs inside the workspace of the created folder of the project created folder, and then include the file from the precompiled object file to this path, and then on the top on the libraries part click edit and type in arm_cortex m4l_math. From there you can recompile your code with the define and the arm_math.h, and you will see that it will be compiled clean. There will be no errors. The sixth step is to enable the waveform for the simulation. In our while loop, we use the arm_cos f32 function. This will display the sinusoidal waveform. Next, the project in general is not a real success. However, it is projected into the right direction of enabling CMSIS DSP functions for filtering signals. The result is expected to be as shown. The original waveform is the distorted signals with noise, and it will be filtered, and all the noise will be opted on, only leaving the clean signals that needs to be used. Due to the complexity of the CMSIS DSP functions, the project was not able to finish. The main code that consists of the CMSIS DSP functions has issues with the library being initialized with multiple type floating point through the command mfloat abilities, which requires hard and soft for this particular project. However, the software IDE compiler does not support both. The project should be enabled through Kale software to support this issue. In conclusion, the filters plays an important role in various big projects, especially adaptive filters. The least mean square algorithm in particular has been chosen to be implemented in this project as an adaptive filter algorithm. This algorithm is widely implemented in various fields due to robustness and simplicity. The ARM Cortex-M4 is used in this project as it can offer high efficiency functionality of signal processing with low cost and low power. That is all from us. Thank you.